Budapest, Hungary, March 1906. The Danube River moved slowly that morning, heavy and silver under the low clouds. On the western bank, a thin young man stood outside his father's engineering workshop, staring at the smoke twisting above the rooftops. To anyone else, it was just smoke, but to him it was motion, geometry in the air. His name was Theodore von Kármán, and before the world would know it, he had already begun calculating the invisible laws that would one day carry airplanes, missiles, and men beyond the sky. At 25, he was already considered one of the brightest minds of the Austro-Hungarian Empire. His notebooks were filled with equations describing how air moved around an object, ideas so advanced that even his professors doubted them. He spoke softly, rarely smiled, and saw the world not as shapes, but as patterns of force. While Europe was still fascinated by steam engines, he was thinking about aerodynamics, the future of movement itself. When the Wright brothers made their first flight in 1903, Kármán studied every photograph he could find. He wasn't impressed by the wood and canvas. What fascinated him was the air itself, the invisible sea every pilot would have to learn to sail. In his mind, he saw it as a living system. Currents, vortices, pressure fields. He would later call it the language of the sky. By 1908, he was designing experimental propellers and wind tunnel models at the Technical University of Budapest. His work soon led him to one of his first great discoveries, the pattern now known as the Kármán vortex street, a repeating wave that forms when air flows around an obstacle. That single equation would become a foundation of modern fluid mechanics. Every aircraft designer still studies it today. But science alone could not protect him from the coming storm. Europe was turning unstable. Nationalism, unrest, and industrial militarization began reshaping the continent. When the First World War erupted in 1914, Kármán was drawn into the conflict, not as a soldier, but as an engineer. He joined the Austro-Hungarian Army's aviation corps, designing improved propellers and even an experimental helicopter that never saw combat. He saw what science could do when it was used to destroy, and it haunted him. After the war, he became director of the Aeronautical Institute at Aachen, Germany, where his work caught international attention. He collaborated with students and engineers from across Europe, pushing aircraft to fly higher and faster. Yet, as the 1920s turned to the 1930s, something darker spread through the laboratories. The Nazi regime began tightening control over science, demanding loyalty, not logic. Colleagues vanished. Jewish scientists were dismissed. Kármán, of Jewish heritage himself, realized that staying would mean silence. Or worse. In 1930, he accepted an invitation from the California Institute of Technology to lecture for a single semester. He packed one suitcase and a stack of research papers. He never went back. When Hitler rose to power, his laboratory in Aachen was absorbed by the German state. His name was erased from official records. In Europe, he was gone. But in America, his story had just begun. At 50 years old, he was starting over in a foreign country with no resources and no political backing. Only his mind. Yet, within months of his arrival at Caltech, he transformed a small wind tunnel in Pasadena into one of the most advanced research facilities in the world. He called it the Guggenheim Aeronautical Laboratory, and his students would soon call him simply the Professor. In that California workshop, he created a new generation of thinkers, young men who would soon design the planes, rockets, and missiles that defined the 20th century. While politicians debated and generals prepared for another war, von Kármán and his team were already designing its future weapons. He believed science would decide the next conflict long before the first bullet was fired. By the end of the decade, his predictions proved right, and as the world descended into war once again, the man who had fled Europe would become the one who taught America how to master the air. Would you trust a refugee scientist to shape the future of your nation's defense? Pasadena, California, October 1936. The California sun burned bright over the small campus of Caltech, but inside the Guggenheim Aeronautical Laboratory, the air was cold and mechanical. the constant hum of wind tunnels, the rattle of engines, and the sharp scent of oil and ozone. At the centre of it all stood Theodore von Kármán, coat unbuttoned, chalk in hand, lines of equations covering the blackboard like a secret language. He wasn't just teaching, he was building the foundation of American air power from scratch. Von Kármán saw the future with terrifying clarity. He warned that the next war would not be won by the number of soldiers, but by the quality of machines. Aerodynamics, Meibais, he said, will decide victory. At a time when many in Washington still thought airplanes were just reconnaissance tools, von Kármán was already designing supersonic aircraft, rockets, and high-altitude bombers. He gathered around him a small group of restless young engineers, men like Frank Molina, Jack Parsons, and Ed Foreman, who were obsessed with the idea of rocket propulsion. In their free time, they ran dangerous experiments in the dry canyons behind Pasadena, mixing chemicals that could easily explode. Locals began calling them the Suicide Squad. Von Kármán didn't laugh. He saw in them what others didn't, the beginning of a new kind of flight, one that would reach beyond the atmosphere. By 1938, he helped the group secure a small Army Air Corps grant to test their rocket systems. The experiments were chaotic. Engines burst, metal burned, and test stands melted, but each failure carried new data. Under von Kármán's guidance, they built mathematical models to predict thrust and stability, something no one else had achieved before. That tiny project would evolve into the Jet Propulsion Laboratory, PL, the birthplace of the American space program. But while the experiments continued in California, the world outside was collapsing. Europe was on fire. The German Luftwaffe dominated the skies, with aircraft faster and deadlier than anything the Allies had. In 1939, von Kármán received a visit that would change everything. A young army officer named Hap Arnold, who would later command the entire US Air Force. Arnold had one question: how do we make American planes win? Von Kármán didn't answer with patriotism or politics. He answered with math. He explained that every plane's performance could be predicted: speed, range, lift, drag, and therefore improved. You cannot outfight the laws of physics, he told Arnold, but you can learn to use them. Arnold understood immediately. He ordered von Kármán to organize a team to study and revolutionize American aircraft design. It was the birth of a partnership that would define the rest of the war. By 1941, as the US prepared for entry into World War II, von Kármán became one of the most powerful civilian scientists in the country. He founded the Aerojet Engineering Corporation, turning experimental rockets into practical weapons. His lab developed jet-assisted takeoff systems, JATO units, that allowed overloaded bombers to lift from short runways, giving the Allies a massive logistical advantage. He also advised Lockheed and North American Aviation on wing geometry, stability control, and compressibility, solving aerodynamic problems that had killed test pilots for years. His mathematical equations predicted where airflow would collapse around high-speed planes, allowing engineers to design wings that could survive near the speed of sound. In meetings, von Kármán was unlike any other scientist. He would walk into a room full of generals, cover a wall with chalk formulas, and finish with a line like, "Gentlemen, this is how you win the war." And more often than not, he was right. By 1943, the United States was mass-producing aircraft that carried his signature indirectly. Not his name, but his theories. The B-24 Liberator, the P-38 Lightning, the P-51 Mustang. Each design had benefited from his aerodynamic principles. Even when he wasn't on the factory floor, his equations were. As D-Day approached, the US Air Force faced a new question: what comes next? The Nazis were developing V-2 rockets, capable of striking London from across the continent. Von Kármán knew that whoever mastered propulsion and control at those speeds would shape the next century. While others saw the rocket as a terror weapon, he saw the dawn of something greater. A bridge between aviation and space. He began drafting a top-secret report for General Arnold, outlining what he called the horizon beyond victory. He described supersonic fighters, long-range missiles, and satellites orbiting the Earth. It sounded like science fiction. But to von Kármán, it was just applied mathematics waiting for funding. In late 1944, his predictions were no longer ignored. He was flown to Washington to help form the Scientific Advisory Group of the US Army Air Forces, its mission to imagine the post-war future of air and space defense. The war wasn't even over, and von Kármán was already planning for the next. He had left Europe to escape destruction, but he ended up designing the very technologies that would prevent it. From the equations in his notebooks to the engines roaring over Europe, his fingerprints were everywhere, unseen but essential. He had transformed the skies above the battlefield. Next, he would change the skies above the world. If you could see the future as clearly as he did, would you use it to build or to destroy? Washington, D.C., December 1944. Snow fell on the steps of the Pentagon, melting into grey puddles under the boots of officers rushing between buildings. Inside, one man sat quietly in a small office, drawing lines across a map of the world. Theodore von Kármán was not a soldier, but the war now depended on his mind. General Hap Arnold had given him an impossible order, to imagine what air warfare would look like in 20 years. Von Kármán's answer became a classified document titled Toward New Horizons. It was more than a report, it was a prophecy. He wrote that airplanes would soon exceed the speed of sound, that rockets would reach space, and that guided missiles would replace artillery. He warned that nations who ignored research would become slaves to those who didn't. Every chapter was filled with equations, but between the lines, it read like a manifesto. Science is the new army. As he worked, reports arrived from Europe. The German V-2 rockets striking London, the jet-powered Me-262 fighters, technologies that confirmed his predictions. America was winning the war. But von Kármán saw something else. The next one had already begun. He convinced the Air Force that victory would no longer come from numbers, but from velocity. The sky is no longer the limit, he told Arnold. The atmosphere is simply the first layer of the battlefield. After the war ended in 1945, von Kármán was sent to Germany under Operation Lusty to inspect captured Luftwaffe laboratories. What he found shocked even him. Wind tunnels large enough to swallow bombers, rocket designs far beyond Allied expectations, and engineers who had been forced to serve Hitler's regime. Among them were men who would later work for both the US and the Soviet Union. Von Kármán studied their research, then calmly wrote, "They have advanced our schedule by 10 years, but we will advance it by 50. Back in America, his influence grew. He helped reorganize the Air Force's entire research structure, creating what would become the US Air Force Scientific Advisory Board, a direct channel between science and strategy. He insisted that every future aircraft be designed not by instinct or tradition, but by mathematics. Under his guidance, engineers mapped the boundaries of supersonic flight, learning where shockwaves formed, where air turned lethal, and where wings could no longer be trusted. His theories led directly to the Bell X-1, the orange rocket plane that, in 1947, would break the sound barrier with Chuck Yeager at the controls. Von Kármán wasn't in the cockpit, but his formulas were in the metal. When Yeager landed, he said, "The plane didn't break the sound barrier. The engineers did." By the late 1940s, von Kármán had become a symbol of America's new identity, the fusion of intellect and power. He attended conferences where generals now spoke in scientific terms, quoting his equations. The US had entered a new era, one where wars would begin not in trenches but in laboratories, yet he remained humble. When journalists called him the father of aerodynamics, he laughed softly and said, "I'm only the uncle." To him, genius was not a gift, but a responsibility. His colleagues described his office as a battlefield of papers, filled with drawings of supersonic wings and vertical rockets. On one wall hung a single photograph, the Wright brothers' first flight, and beneath it he had written, "From dream to discipline." Von Kármán's greatest legacy was not a machine, but a mindset that science, when guided by reason rather than fear, could keep humanity one step ahead of its own destruction. Would you trust knowledge to guard your future, even if it came from the same science that once built your enemy's weapons? Pasadena, California. June 1946. The war was over, but the laboratories of Caltech were louder than ever. Outside, American soldiers were coming home. Inside, scientists were already preparing for the next frontier. The smell of oil and ozone still filled the air, and the sound of turbines echoed through the Guggenheim Aeronautical Laboratory. But now the questions had changed. They were no longer about dogfights or bombers. They were about what lay beyond the air itself. Theodore von Kármán walked slowly through the hangar where his young engineers tested experimental rocket engines. Each explosion, each burst of flame, carried him further from the world of propellers and wings, and closer to something entirely new. For the first time in history, the word space was being spoken in the language of physics, not fantasy. He gathered his former suicide squad, Frank Molina, Jack Parsons, Ed Foreman, the men who had once risked their lives testing rocket fuel in the desert. With government funding secured from the newly reorganized Army Air Forces, their project had evolved into a permanent institution. The Jet Propulsion Laboratory, JPL. In a modest building at the base of the San Gabriel Mountains, they worked day and night, surrounded by blackboards, pipes, and the smell of scorched aluminum. They tested small rockets, solid and liquid fuels and guidance systems. The results were unstable, dangerous, unpredictable, but full of promise. Von Kármán's leadership style was unlike any other. He didn't shout, he calculated. He didn't demand miracles, he asked for precision. The laws of nature, he said, do not change because we wish them to. They change because we learn how to use them. By 1947, as the Cold War began to harden between the United States and the Soviet Union, Washington realized what von Kármán had warned years earlier, that science was now the real battlefield. The Soviets were capturing German rocket engineers, led by Wernher von Braun, while the Americans rushed to organize their own. Von Kármán was brought to Washington again, not as a refugee or an outsider, but as the architect of America's scientific defense. He became the head of the Air Force Scientific Advisory Board, an elite group that connected the military with universities and laboratories across the country. His goal was simple but revolutionary: to build a system where every future weapon, aircraft, and missile would be guided by the logic of physics, not politics. At JPL, his teams developed early guidance computers, gyroscopic stabilizers, and engines powerful enough to break free from Earth's pull. Small steps toward a destiny no one had yet named. Von Kármán watched each success quietly, his hands folded behind his back, knowing they were building the bridge between war and space. Meanwhile, the newspapers spoke of a different kind of war. The Iron Curtain, the Atomic Age, the race for supremacy. The world that had once fought with rifles was now arming itself with equations. Every nation that had once built tanks was now building laboratories. Von Kármán called it the Age of the Engineers. In 1948, the Pentagon released part of his classified report toward New Horizons. It read like prophecy. The Air Force, following his model, created a new research division dedicated to jet propulsion and long-range missiles. The ideas that had seemed wild in 1944 were now official doctrine. He knew exactly what this meant. The future of flight would no longer be measured in miles per hour, but in escape velocity. That same year, von Kármán received a message from the Office of Naval Research, requesting his advice on high-altitude flight. His response was direct. The time has come to stop thinking of the sky as the limit. It is the beginning. By the early 1950s, JPL was experimenting with sounding rockets. Small, powerful launchers, capable of carrying instruments to the edge of space. Each test was an act of faith. Most exploded on the pad or vanished into the desert sky. But data began to flow in: air pressure, temperature, cosmic radiation. For the first time, science was touching the boundary between Earth and the stars. Von Kármán often walked through the lab late at night, checking on the young engineers who refused to sleep. He would quietly correct their equations or leave small notes in the margins of their designs. "Do not forget," one note read, "that every rocket is a question thrown at the universe." He wasn't just a scientist, he was a philosopher of technology, one who believed that knowledge had to serve humanity, not rule it. "The problem with power," he told a journalist in 1951, "is not how to obtain it, but how to deserve it." In 1952, the Air Force published his final public report on supersonic flight, confirming what he had predicted nearly 2 decades earlier. Aircraft would soon travel beyond Mach 1 regularly, and rockets would be capable of reaching orbit. But even as America celebrated its technological triumph, von Kármán saw danger in the triumphalism of politicians. "The laws of physics are not patriotic," he said. "They will serve whoever understands them best." By the mid-1950s, his health began to decline, but his mind was as sharp as ever. He advised the RAND Corporation, contributed to early missile defense studies, and continued to visit JPL, which now employed hundreds of scientists. The laboratory he had founded with a handful of dreamers was becoming the cornerstone of America's new frontier, space exploration. Then came October 4th, 1957. A single metallic sphere, the Soviet Sputnik, rose into orbit and sent its beeping signal across the world. America was stunned. The race to space had begun, and von Kármán, now in his mid-70s, was one of the few who wasn't surprised. He had predicted this exact moment in his wartime report. When reporters asked him how he felt seeing the Soviets beat America to space, he simply smiled. "Competition," he said, "is the engine of progress." He was invited to Washington again to help reorganize the country's space research efforts. Out of those meetings and out of the institutions he had built, a new organization was born, the National Aeronautics and Space Administration, NASA. Von Kármán had lived long enough to see his theories become the backbone of 2 revolutions, the air age and the space age. Yet even then he refused to call himself a visionary. "I am not a prophet," he said. "I am an engineer. I do not predict the future, I calculate it." As the Cold War expanded and the rockets grew taller, von Kármán returned often to Caltech to watch his students, now the leaders of JPL, prepare the first American satellites. He would stand at the edge of the launch pad, hat in hand, eyes fixed on the sky, and whisper the same words he had written decades earlier. From dream to discipline. He had once fled Europe to escape destruction. Now his work reached into space, carrying the hopes of the same world that had once been torn apart. Would you believe in science this much, if it meant changing not just how we fly, but what we are? Pasadena, California, spring 1960. The Jet Propulsion Laboratory was no longer a dusty shed in the desert. It had become the beating heart of America's space age, white-coated engineers, buzzing control rooms, and antennas pointed toward the heavens. But in the corner office, the old man who had started it all sat quietly, reading. Theodore von Kármán was nearly 79, his body slower, his mind still faster than any computer he had helped to inspire. He had seen his ideas take flight, quite literally. Supersonic jets, intercontinental missiles, experimental spacecraft. Every one of them carried a trace of his equations. His vortex streets, his boundary layers, his calculations of lift and drag. They were invisible fingerprints on the sky. Visitors came from around the world to meet him. Some were generals, others young scientists, who wanted to see the man whose math had turned fantasy into flight. When asked if he was proud, he usually smiled and said, "Pride is for pilots. Engineers build, then move on." That same year, the US Air Force invited him to attend the test flight of a new jet, the North American X-15, a rocket-powered plane that would touch the edge of space. The aircraft climbed higher and faster than any human had ever gone, and when it landed, von Kármán whispered, "We are already halfway to the moon." He was right. Within a decade, the first astronauts would walk on the lunar surface, and every calculation of thrust, temperature, and lift would trace back to principles he had laid down half a century earlier. Despite his fame, von Kármán remained the same quiet, stubborn mathematician from Budapest. He refused luxury, preferred public transport, and still carried a slide rule in his coat pocket. When reporters tried to make him a celebrity, he corrected them. Celebrities are made by the press. Engineers are made by their results. But even he could not escape recognition forever. In 1963, President John F. Kennedy presented him with the National Medal of Science, the first ever awarded in the United States. Standing in the White House, the old scientist bowed slightly as Kennedy said, "Few men have ever influenced the advancement of science and flight as profoundly as you." The room applauded. Von Kármán simply replied, "It is not me you should thank, Mr. President. It is the next generation." That same year, tragedy struck the world. Kennedy was assassinated in Dallas. The image of the young president shaking hands with the old engineer became one of history's last photos of both men alive. Two visions of progress, briefly intersecting. By the mid-1960s, the Cold War was raging, and the space race had become a political obsession. Von Kármán watched from afar, half proud, half uneasy. He supported exploration, but feared competition would turn science into propaganda. Space should be a laboratory, he said, not a battlefield. At Caltech and JPL, younger engineers still called him the professor. They invited him to lectures and launch tests, where he often stood quietly, hat in hand, staring at the sky. One student once asked, "Professor, what do you see up there?" He answered, "The same thing I saw when I was a boy. Motion, waiting to be understood." As his health declined, he returned more often to his small house near the Arroyo Seco Canyon. He spent his mornings writing letters, correcting manuscripts, and advising governments from his study. His correspondence stretched across the globe, from Washington to Paris to Beijing. Even the Soviet Academy of Sciences invited him to collaborate, calling him a man whose science belongs to all nations. That was perhaps his greatest achievement, not a single invention, but a bridge between enemies. His equations transcended borders, serving both sides of a divided world. In 1964, von Kármán suffered a stroke while attending a conference in Aachen, Germany, the very city he had fled 3 decades earlier. He died a few days later at the age of 81. The New York Times wrote he gave shape to the invisible. His ashes were brought back to America, and a memorial was placed near the laboratory he built. Etched into the stone were his own words, "Scientists study the world as it is. Engineers create the world that has never been." It was not arrogance, it was truth. In the years that followed, his influence only grew. NASA named an award after him, given to engineers who push the limits of possibility. Caltech's main aeronautical library bears his name. His students went on to lead the Air Force, NASA, and countless aerospace companies. Each of them carried a piece of his philosophy. That calculation is courage, and that precision is the purest form of faith. Even the moon carries his signature. In 2019, when China's Chang'e 4 spacecraft landed on the far side of the moon, the site was named Von Kármán Crater, a silent tribute to the man who had helped humanity learn how to reach it. He had started his journey as a refugee from a fallen empire and ended as a name written on the surface of another world. Today, his equations still guide every jet that breaks the sound barrier, every rocket that escapes Earth, and every spacecraft that enters another planet's orbit. He proved that the laws of motion are not barriers, they are invitations, and though the machines have evolved, his principle remains the same. There is no magic, only mathematics we have not yet learned. He never built monuments, never led armies, never sought power. He built something far greater, a path through the air itself. Theodore von Kármán didn't just master the wind, he defined it, and the world, for all its progress, is still catching up to his imagination. So next time you see a jet slice through the clouds, or a rocket light up the night sky, ask yourself, would any of it exist if one man hadn't looked at the wind and decided to measure it.